looks like we're only missing maybe one person. That's great. Great. Good job. All right, let's take a look and see what Buzz is going to show us this week. Let's go to our grade screen as usual. Oh, it didn't. It went to the bottom. No, grade screen. Okay, this weekend is October 5th. Whew, man, already. You should have 2.01 through 2.04 done. So this class moves at a pretty good pace. We've got graphing transformations this week, and then the practice test. So we only have one lesson this week. So we have that, the practice test, and then next week we'll take the module 2 test. So we just have one lesson left. And of course, the practice test, you can take the practice test as many times as you want. That just helps you know, am I ready to take the test? If you take the practice test and do well, then you're probably ready. If you take the practice test and bomb it, you probably need to review the practice test and go say, uh-oh, what did I miss? You know, if you don't know how to look and see what you missed, let me go over this practice test up here. If I go click on that, it just shows me my score and when I turned it in and all that kind of stuff. But you can click on this little menu. It says questions right there. And then you can actually see all the questions. So you got that one right. You got that one right. Got a little green check mark, let you know. Got that one right. So it just lets you know what you got right. Oh, this one's wrong. The correct answer is this. I didn't answer anything. See, I didn't answer anything on that. But select an answer. It'll tell you which the correct answer was, so you can review and say, why did I miss that? So yes, you can go look at anything that you've taken and check out, what the questions were right there. So all right, so we're going to look at the graphing transformations lesson this week. And since we're graphing, that's probably going to be Desmos. So let me go ahead and open up the Desmos window. You ready for that? Okay. 2.05. Graphing transformations lesson. Scenic overlook. So, an asset for students of this course is to be able to visualize the shape of a graph by seeing the basic shape of the graph and using transformations. Like in the linear function, for example, we know the basic graph, f of x equals x, is a straight line through the origin. So we can go ahead and throw that on there. So they're saying f of x equals x. That is the most basic linear graph, right? The most basic. And for ax plus b, that defines the slope and the value of the y-intercept. So let's see, it'll let me have a slider for that too. Ax plus b, and I can have a slider for that. So if we change the a, it changes the slope. Now it's no longer the basic graph. Let's see if I put that at 0. So there is the basic graph. If it becomes anything besides 1, it changes the slope. If it's a negative number, it goes down. It can get really, really, really steep, either direction. If we go back to just the basic and I change the b, that just changes where it crosses the y-axis, right? So it's easy for us to visualize what the graph looks like with the mx plus b formula, knowing that the b will affect where it crosses the y-axis and the a is going to affect the steepness of the graph. So those are just transformations from the basic y equals x. So summary of graphs of common functions. So let's look at the 6 most common functions in algebra, which is the constant functions. Now, constant functions is just like, let's see, y equals 3. That's a constant. It's just a number. It never changes. The graph is just 3 all the time. That's the constant function. The identity function, the absolute value function, the square root function, square root function, and cubing function. And I have a link right here that has all of these on one document. It's still loading. Oh, there it is. So there's the constant function. The identity function is just the linear y equals x. F of x equals x. That's the identity function. The squaring function, that means it's a quadratic, it's a parabola, it's x squared. The most basic being this shape right here, goes through the origin. The cubing function is x to the third power, and it goes through the origin, but it goes down to the left, up and to the right. The square root function, in its most basic form, notice it doesn't have negative values because we can't have a negative square root. And it doesn't have any negative x's because you can't take the square root of a negative number. So it's only from the zero origin into the positive areas. And then the absolute value. Again, you can't have a negative absolute value. You can take an absolute value of a negative number. That's why we have negative x's, but there's no negative y's. Because if you take the absolute value of something, it has to be 0 or greater. So that's why that graph looks like that. So those are the 6 most basic ones that we generally use in mathematics. Either a constant or just an x or an x squared or x to the third, sometimes square root, sometimes absolute value. We could wander off into other graphs, but this is where you'll find yourself most often. Let's talk about horizontal and vertical shifts. So these transformations are created by adding a constant either to the entire function or to the argument of the function, like the input of the function. So we know that the graph of the function f of x equals x squared has a point 0, 0. So let's put that out there. Y equals x squared has the point 0, 0, right? That is the turning point, the vertex. If we want to shift the graph up or down, we can simply do that by adding a number to the end, plus 4 or minus 4. We can shift it up and down by adding a number. If I want to make it a variable here, just add a slider. We just go up and down on whether that's a positive or a negative number. Let's see it more. Right? So that's a transformation by adding a number at the end. So it's x squared plus c, where c is the point where it will cross the y-axis. So in addition, so therefore the addition of a constant to a function moves the graph up and down the y-axis. And what we're going to see is it doesn't matter if it's x squared, if it's x to the third, that still does the same thing. Adding that constant at the end is going to shift it up and down. What if it was an absolute value equation? Let's do that. No, that's not how. Yeah, that's how I did it. Absolute value of x. Look, again, adding a number on the end just shifts where it crosses the y-axis. It does not matter which one of these functions we use. Just adding a number to the end of it will always move it up and down and affect where it crosses the y-axis. We can shift the graph to the left or right along the x-axis by changing the value of x by a constant. So let's go back to our x squared equation. X squared. I don't have an a now. If we want to move it left or right, we change the value of x by a constant, which means I'm going to put it in parentheses, just the x, because I say if I want the x to move left or right, if I add 2 to the x and then square it, look, it moved it to the left 2 values. To get back to x, we'd have to subtract the 2. It's left 2. If we add 2, it'll take us back to the origin. We moved it off by 2. So if we added 2, it would take us back where we started. If I subtract 2, it moves it the other way. If I subtract 4, it moves it 4 spaces. It'll move it however, whatever number I put, and it'll go left and right, whether it's positive or negative. That determines left and right. So we have 2 things we can do to translate. We can move it up and down by adding a number at the end, or if we add or subtract a number to the x, wherever the x is in the equation, it'll move it left and right. So doing both of those at the same time would move it up and down and left and right. So see the text for the vertical and the horizontal shift rules. So we may go look at that. But yeah, x minus 5 squared shifts it 5 units to the right. So test your skills. This doesn't have a solution. It says review the example shown in the text. What effect does the constant have on each of these graphs? So I'm going to open up the chat just to give us a chance to kind of get in here and dig into it a little bit, make sure we understand transformations. But if I have x squared minus 6, what is that minus 6 going to do to the graph of x squared? Alexander's on that immediately. Yes. Surprise, got it. Yeah, the minus 6 is just going to move it down 6. It's going to take the original graph of x squared, which goes through the origin, and it's going to move it down 6. How about over here, where we take the minus 6 and we put it inside the parentheses with the x and then square it? To the right 6, the right 6. Exactly. Yeah, the minus 6. So you can't remember if we went minus 6. It moved it to the right over here. Instead of being at the origin, it's over at 6, 0. Very good. How about taking just a linear equation and adding 3 to it? So this is just a line. We're adding 3. Yeah. Doesn't matter what kind of equation it is. If we just add a number to the end, it does go up 3. Yes. And if we take it, the plus 3, and put it in the parentheses, yeah, it goes left 3. And you think about that, it's like, well, how do I know this isn't moving at left 3 since it's with the x? Because if you put it in parentheses, it'd be with the x. Well, if you think about that, see, that's a good question, because then y equals x would just go through there. And if I add 3, I'm raising it up 3. So how do I know it didn't just move it to the left? If I put it in parentheses, well, it did. It also moved it to the left. It applied both rules. If I put it in parentheses or not, it moved up 3 and it moved left 3 because it's linear. It's linear. That's why you could look at that one either way. If I put it in parentheses, well, I moved it left 3. If I don't, I moved it up 3. But either way, it's the same graph because it's a linear graph. It doesn't really affect it. Plus 3 or plus 3 is still just plus 3 for a linear graph. All right, reflection shifts. So another graph based on common graphs is called a reflection. This is a mirror image, right? That's what we think. A reflection, we see our reflection every time we look in a mirror. That's a reflection. It's created by the negative value of a function. So you would put a negative in front. Negative. And this one reflects it downward. So where it used to go up from this point and go through 3 up here, now it's reflected downward. If we take out the plus 3 and just make it x, reflected it downwards and over the x-axis, everywhere it went up, now it goes down. Here's the original. Instead of going up, it goes down. It's just a mirror reflection, like you're looking at a lake right there on the x-axis, and these beams are coming down, and we can see them reflected downward. X squared. I'll need the. There's the original x squared and the reflection going down. Exactly the same shape, just goes down instead of up. Reflections. Non-rigid transformations. Okay, let's talk about the difference there. Non-rigid transformations. It really means exactly what the word tells us. And when we think of rigid, we think of very firm. You can't change it. Like a steel beam is rigid because it's, you can hit it and whatever. It's not going to be. And we can move it. We can take that steel beam and push it over there, but it still looks exactly the same. It's still the same shape. We've just moved where it's at. And so these transformations we were just looking at, all they did is take the parabola and move it up, or we could reflect it down, or we could move it over, but it's still the exact same shape. We didn't squish it, we didn't stretch it. Those are rigid transformations, which means that doesn't change the shape. The shape is rigid. The shape stays exactly the same. The line was still the line. The absolute value is still the absolute value, whether we shift it up or down. It did not change it. So those are called rigid transformations. Horizontal and vertical shifts, reflections. The graph stayed the same. But we can do non-rigid transformations. So that's what it's looking at next. It's talking about a non-rigid transformation that causes the shape to be different than when it started. And that is caused by multiplying the function by a value other than 1 or -1, because 1 or -1 doesn't change anything. But if we take this x squared equation and we put a number in front of it to multiply it, times 3, well, now that's a different shape. We have changed the shape. It's not the same shape anymore. Or 0.2 makes it wider, all right? 0.2. Multiplying it by a number, taking the function and making it a different shape. It says use your graphing calculator to graph each of the following, and let's see what's the differences. Oh, this is a good one. So we have absolute value of x, 3 times the absolute value of x, and 1/3 times the absolute value of x. So we can do that right here. Let's open up the little menu down here and grab the absolute value. See, y equals. There's the absolute value symbol. So absolute value of x. All right, that was the first they wanted. And now they want 3 times the absolute value of x. Okay, that's the green one. The green one is 3 times. Absolute value of x, 3 times the absolute value of x. And then they wanted 1/3 times the absolute value of x. Okay, so the original one is right there. If we take it times 3, it goes up a lot faster. So what's really going on when we take it times 3? Well, what happens is this point right here, where the x was 1, 1, 1, the y value gets multiplied by 3. So instead of 1, 1, it's 1 times 3 is 3. So now it's up at 1, 3. Because we said take the absolute value of x and multiply it times 3. If we do the 1/3, we took 1 and divided by 1/3. So now it's down here at 0.33333 because we multiplied it by 1/3. So that's why it looks wider, because all of these y values that was on the original blue line, we only have 1/3 of them now. So instead of being at 9.9, it's down here at 9.3 because we took 1/3 of that absolute value of x. The absolute value of 9 is 9, but you would take it times 1/3, so they go 3. Where the other one's 3 times, so it's way up at 27 when we get to 9. There it is. It's at 27. So that's why putting the number out front makes it either skinnier or wider. And if it's larger than 1, it's going to be skinnier because it's going up faster. Smaller than 1, the values come down. All right. So that's the transformations. So, and that's the whole summary of this lesson. Just looking at what these transformations do. So we can look a little bit into their examples down here. Talks about these functions all being different. You look at their graphs, talk about rigid transformations, leave the size and shape unchanged. It just moves it around on the graph. Non-rigid are ones that distort the shape, changes it. Let's see. Once you graph these functions and look at them to see what the +3, the +1, I think we got a good idea what the +3 and the +1 does with the x, without the x. Replacing x by x minus c shifts it horizontally. Replacing y by y minus c shifts graphs vertically. If you want the rules right here to write in notes, if you're not sure, if you have the x in parentheses and change it by a value that we subtracted C from it. That's going to move it right. So here's a little chart you can put in your notes. You can print this as your notes if you have a printer. Now C is a positive number. It puts that there. Let C be a positive number, positive real number. So if you have X minus a number, it's going to go right by that number, C. If you have X plus a number, it's going to go left. And then vertically, if we stick it at the end, plus is going to go up that by C units, minus is going to go down by C units. So it's just talking about the differences in there. So that's all pretty straightforward stuff. And then the reflections that we looked at, just putting a negative on there. So let's look at the assignment on this. This is nothing new to us. In Algebra 3, we've seen translations for 3 years here. Let's see it. Start C. Describe how the graph of y equals x squared can be transformed to y equals x squared plus 8. So if we start with y equals x squared, what happens when we have y equals x squared plus 8? So you shift the graph up 8 units, right 8 units, left 8 units, or down 8 units. And again, if any of these confuse you, put them on here. Right? Go look at it. Graph both of them and see what it did if it confuses you. But I think most often you're going to have this pretty quick. Describe how the graph of y equals x squared can be transformed to x minus 16 squared. Does it go down, left, right, or up? 16 units. Y equals x squared to x plus 9 squared minus 3. We got two different things going on there. There's go left 9 and down 3, down 9 and left 3, right 9 and down 3, up 9 and right 3. How about this? The square root of x equals negative square root of x. Does that reflect it across the y? Does that reflect across the y and then across the x? Are there two reflections going on? Does it just reflect it across the x? Or does it shift it left 2 units? Please don't answer that one. Don't say it's left 2 units. And then the last one is describe the transformation of the graph of f on the g as either a horizontal or vertical stretch. Oh, let's talk about that terminology. Horizontal or vertical stretch. So let's just look at an equation. Let's just do x squared. Okay, so this is our original equation, x squared. And it says it's going to be a stretch. It's either going to stretch it vertically or stretch it horizontally. So let's look at the differences. If I put this number on it, and there's our new graph in green. I'm going to change it to red. That's probably a little clearer to see there. In red. So is that horizontally stretched or is that vertically stretched? You're like, well, that's what confuses me, Mr. Brock. Well, think about stretching means. If we were going to horizontally stretch it, all right, if we think about what it means to stretch it, it means pull it farther that way, right? So if this was a piece of wire that you had to shape like a parabola, and we said we want to horizontally stretch it, well, that means we're going to grab it and we're going to pull it horizontally, and it's going to get wider. It's going to get wider because we've horizontally stretched it. So then you think, well, what's a vertical stretch then? Well, we got that same shape and we pull it up to where it goes up faster. It's what we call a horizontal stretch because instead of it being here, we've pulled it up to here because we're pulling it to where it goes up a lot faster. So a vertical stretch, they're talking about it got skinnier. It was going out here, but now we've pulled it where it goes up a lot faster. It's a vertical stretch. Right. Yes. And this one I have on here, you guys got that in the chat. I did a vertical stretch on that parabola when I put a 6 in front of it. It made it go from like this to like this. So horizontal, vertical. Right. So don't let that confuse you. Sometimes they'll use the word shrink as well. So if we look at what I just did with this graph, it's a vertical stretch, but it could be considered a horizontal shrink because it's not as wide. We've pushed it in. horizontally it's been pushed in. So both of those terms describe the same thing that happened there. It is a vertical stretch, but it's also a horizontal shrink. So just watch the terminology that math questions put. Which word are they using? Are they using shrink or stretch? And think about that. A vertical stretch is a horizontal shrink. And the same thing with a vertical shrink. Vertical shrink means it goes up slower, but that's also a horizontal stretch. Those are the same things. So don't let that confuse you. They talk about a vertical shrink or horizontal stretch. That's the same thing. Stretching it out so it doesn't go up as fast. Vertically, it's now shrunk down, but it's also wider horizontally. So it does get confusing because depending on the unit or the textbook or whatever, some of them may like to talk about shrink and some of them like to talk about stretch when really they're interchangeable. You just have to pay attention whether it's vertical or horizontal. So yeah, don't let that throw you off. So that last one is this horizontal vertical stretch? And they're asking about a stretch. So I don't know if some of the questions ask about a shrink or not, because again, you may not have this exact same question, but hopefully they all use the word stretch since this one does, and it won't get real confusing. All right. Yes, I know I'm leaving. So that is the only lesson we have to cover this week because now we have the Module 2 practice test. And we'll look at it. And I'll point out that, again, I have a video of me taking the practice test. So if you take the practice test and you don't do well and you can't figure out why something's wrong, come here, click on this. And here's a 43-minute video where I did every single question. And of course, you can maximize it, make it full screen if you like to. But you can skip forward. You don't have to watch the whole thing because if you take the practice test and you did great on the first 10 questions, well, don't watch the first 10 questions there. I'm going to skip ahead. What problem am I on here? This is problem 8 and 9 on the screen, so I probably need to go ahead a little farther. I'm looking for where Mr. Brock did question 10 or 11 or whichever one I need. So skip ahead, whatever you need. There's problem 10 right there. So if you got the first 10 right, maybe you start here on number 11. So you don't have to watch the whole thing again, like I said. But I work everyone, and as you can see, I'm graphing some of them. Some of them I'm putting on paper. I'm going through the whole practice test. So that is for you to use as a tool after you take the practice test. Take the practice test first, though. Let's start and take a look at it. Determine whether this graph is the graph of a function. Oh, just there it is. We don't have the equation, but you have a graph. And remember, with a graph, you can do the vertical line test. Is there only one y for each x? Or if you draw a vertical line, will it touch the graph twice? What is the domain of this function? What x's are allowed? And you're like, well, it's just 4 over x squared. Is that, can it be any x? We're dividing 4 divided by x squared. It can't be just any number. Find the range. So the range depends on if I substitute an x in there, what possible y's could I get? And think about every single x you can put in there. And you may want to graph it, and a graph will show you the range, right? When we look at this, the range of this is from 0, and it does equal 0, from 0 to infinity. If we had this graph, the range would be from 2. It doesn't go below 2, right? There's no y's exist below 2. It exists at 2. That one's there. When x is 0, it does equal 2. But it can't be anything below that. So it just depends on your graph. And you could graph this to figure that out. Or if you could look at it mathematically and understand what's the range of that function. What's the domain? What are all the possible x's you could put? Can you put 0? Can you put 7? Can you put -7? Can you put 10? Can you put -10? What's the limitations? Because it's under a square root symbol, there are limitations because we cannot take the square root of a negative number. But this is just x by itself, so you can't just say I can't have a negative x, because if I have a -2x, 7 plus -2 is the square root of 5. That's still a good number. So x could be a negative number, but there's a limit to what x can be, because at some point 7 plus x gets to be a negative number, and now we got a problem. Oh, this one can confuse people. Determine the intervals in which this function is increasing, decreasing, and constant. Oh, that's a good one. I want to look at that one. So if we graph that, and the graph would be something like this. Oh, I guess it would actually be, let me put it like this instead. Okay, that kind of looks like the one on the. Where is this increasing, decreasing, or constant? And when it asks that, you would say like from negative infinity to 0, it would be increasing, right? It talks about, you have to answer it using the x's. I think it shows that. Yeah, increasing on x is less than 0, decreasing when x is greater than 0. Or is it increasing when x is greater than 0 and decreasing when x is less than 0? Or is it increasing everywhere or decreasing everywhere? When we talk about whether a graph is increasing or decreasing, think of it like reading a sentence. We always start on the left and we go to the right. So if the graph starts on the left, are the y's increasing or decreasing? And at what point does that change? Over here, the y is negative 5.5. Over here, it's negative 5.1. Over here, it's negative 4.5. Over here, it's negative 3. Here it's negative 2. Here it's negative 1.5. Here it's 0.73. Does the y ever decrease? Is that y ever getting smaller? Is there ever a point on this graph that it's decreasing? Now, if I have this graph, y equals x squared, this one's a lot simpler to look at, to say, okay, the y is 18. Now it's 17. Now it's 13. Cancel. That y is getting smaller. So this is decreasing, 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 decreasing. Oh, wait, it's not decreasing anymore. Now the y is getting bigger. Look, it's going up. It's 9, it's 12, it's 15, it's 18. So this one, this graph, it's decreasing when x is less than 0. See, because x is negative 0.5, is negative 2. Over here, when x is less than 0, it's decreasing the whole time. Then when it gets to 0, it's constant for just a second. Right there, it's constant. But after, when x is greater than 0, the y is going up. So this one's decreasing when x is less than 0 and increasing when x is greater than 0. So what's this one? Which is what this one is. I don't know what yours looked like on your test, but that's kind of what this looks like. Estimate graphically the local maximum, local minimums. Remember, we looked at that. So if we have an equation like 4x to the third minus 2 2x squared plus x minus 1. Oh, I don't even like that one. That's a blow up there. Is there a local minimum and a local maximum? Yes, right here, it looks like it's higher than both sides of it. Negative 2. Yep, that's larger than negative 2. That's larger than negative 2. That's a local maximum. That's a local minimum. Desmos marked it for me. So when x is 1/3, 0.33333, that's a local minimum. It's not the minimum because there's smaller y's down here, but for this area, it's the local minimum. So you got to look at yours and see, does it have local minimum, maximum? Where are they at? Estimate it graphically. Which on mine is 0.333 is a local minimum. Negative 2.07. Determine, is this even, odd, or neither? Remember how we do that? let's review that real quick. If I want to know if an equation, let me get a sheet of paper here. So I've got this equation. And my equation is going to be 4x to the fourth minus 2x squared plus 1. And I want to know, is this even or odd or neither? Well, if I substitute negative x into there, 4 times negative x to the fourth minus 2 times negative x squared plus 1, and then simplify this, let's see what I get. Negative x to the fourth power. So that's negative x times negative x times negative x times negative x. Negative x times negative x is x squared. If I take x squared times another negative x, that's negative x to the third. And then I take it times another negative x, I'm back to positive because it's negative times a negative. It's x to the fourth. So this is just 4x to the fourth. And negative x squared, that's just negative x times negative x, which was x squared. So that's just a positive x squared. So I got negative 2 times a positive x squared and a plus 1. So f of negative x is exactly the same. There's not a single difference between there. This is an even equation. Same. It's even. Now, if we do this, let's get another one. Let's make it 4x to the third minus 2x. I'm not going to put a plus 1 on it. I'm just going to leave this. And I substitute negative x. So it's 4 times negative x to the third minus 2 times negative x. Negative x to the third. Negative x times negative x times negative x. Negative x times negative x is a positive x squared. If I take that times a negative x, that's negative x to the third. So this becomes negative x to the third times 4. So f to the negative x equals negative 4x to the third, as we took 4 times negative x third. And negative 2 times negative x is positive 2x. So when I look at this is now a negative when it was a positive, and this one's a positive when it was a negative. This is an odd equation. I don't mean that's peculiar, just all opposite. All the signs changed. All of it's opposite. And if we have f of x equals 4x to the third minus 2x plus 1. I'm going to put that plus 1 on there now. And I substitute negative x. 4 times negative x to the third minus 2 times negative x plus 1. Well, we know that this simplifies to that. So this is negative 4x to the third. Negative 2 times negative x is a positive 2x plus 1. Well, look, this was a positive, it's a negative. This was a negative, it's a positive. This was a positive, it's still a positive. Let's do it that way. This did not change. This one is neither. This one's even, this one's odd, this one's neither, because the oddball, this changed, this didn't. If everything stays the same, it's even. If everything becomes the opposite sign, it's odd. But if some do and some don't change, it's neither. Just as a reminder on how that works. Nice reminder there. So that's how you determine if that's even, odd, or neither. And also you can look at the reflection, but I want to do it algebraically way. Find f times g of x. Multiply those together. F times g. Find f plus g. Add these two together. F of g. You substitute g into f and then simplify. Find a f and a g so that when you do substitute g into f, it looks like this. And there's more than one right answer, but I'm sure there's only one of these that are correct. There's more than one way to do that, but they're looking for a specific way that'll work here. So you can just take like this g of x, substitute in there and see if it looks like that. Take this g of x, substitute in there, see if it looks like that when you simplify it. And see which one of these works. Find the inverse. Remember the steps to the inverse. First, you change this to y equals. Then you swap the x and the y. Then you solve for y. And then you put it back into function notation. Or maybe it's not a one-to-one function, so it doesn't have an inverse function. Find the inverse of this function. Find the inverse of this function. Is this one-to-one? And one-to-one means every x only has one y and every y only has one x. That's what one-to-one means. One y to one x and one x to one y. Let's see. Describe how the graph of y x squared can be transformed to the graph of the given equation. So yx squared is y equals x squared minus 14. Does it go right, up, left, or down? So that's the lesson we just looked at. Same thing. So altogether, there are 20 questions. Oh, number 19 is one of those stretch ones. Is this a vertical or horizontal? So you type in the word vertical or the word horizontal. Use lowercase letters. You can copy if you want. If you think this is vertical, copy that and paste it. So if you capitalize it, it'll probably count it wrong if you have the right answer. And here's one of those. Confirm that they are inverses by showing that f of g equals x and g of f of x equals x. So you have to do both. You can't just show one. And here's the two equations that's wanting to say, we believe these are inverses. Can you confirm that by doing it mathematically? And use the insert equation button. Again, if I'm doing the cubed root of x minus 4, I'm not sure how you would show that. Would you do a 3 root x minus 4? I'm not sure how you would show that. But with the insert equation button, you can click down here and there's a bunch of symbols you can use. And if I want to say the third root, look, there's a y root of x. This is square root right here. If I type that, that's a square root. Square root of x, x minus 4. See, that's a square root. But if I click the button right next to the square root, and it says, okay, what root do you want? Well, I want the third root, and I want it to be, instead of x, I got to put it in parentheses, so it puts it all together. And look, it's the third root of x minus 4. It looks just like that. So use the insert equation button. So, not button, button. There you go. Use that button right there. Insert equation. Big difference, because I'm not sure you'd have trouble making third root there. So, okay. Test week next week then, right? Because we're doing the practice test this week. So you have one graphing assignment on translations, which I don't think will take you very long. I hope not. And then the practice test to be ready for next week's test. So again, the practice test is a practice grade. Doesn't affect, if you bomb it, doesn't affect your semester grade. If you do great, doesn't affect your semester grade. It's just there for you to take it to know, okay, I understand this unit. I'm ready for the test next week. Or, oh my goodness, I thought I knew more of this. Let me look at my notes again. Do I need some more notes? Maybe I need to go back to the lesson summary and copy some more notes because I do not know what I'm doing. Maybe I need to come see Mr. Brock on Thursday and say, okay, I took the practice test and these 3 problems here, I'm totally lost. No problem. I'm happy to help. That's why I come to class on Thursday. Okay, guys, you got the rest of the period to, you may be able to finish the practice test even. You can currently get the assignment this week done. Jump in there and get that done. It should be just the 5 graphing questions, and then you got the practice test. If you're behind on anything, of course, get that done first before you take the test next week. You could probably go ahead and do this lesson today, even if you're behind, because it's about graphing, and you've been doing that for years. Practice test, you probably ought to wait till you get caught up on the other assignments, just so you know how to do all the things that's on the practice test. And then next week we'll just have the test, so that'll be short and simple. So there you go. Use the rest of the class. I'll be here if you want. You don't have to stay in class if you want to work on it on your own. But if you want to hang around, if you think you'll have questions, I'll be here. So have a great week. If any of you have a grade below 70, I'll see you Thursday. RTI's already filled out. And I did fill it out. We're doing it on Fridays now. I was gone Friday, so I filled it out on Thursday. So if you turned in a bunch of stuff this weekend and got your grade over 70, I'll count your present. I won't. Even if you're an RTI, if your grade's over 70 and Buzz, I'll count your present. You don't have to come. So check your grade and Buzz. Make sure it's above 70. And we'll see you later. So I'll mute myself if anyone wants to hang around and work.